So the conservation of momentum says that, well, like conservation laws, the total amount of something before is equal to the total amount of something after. In this case, we're talking about momentum, which is mass times velocity. Well, as it pertains to, say, cars, when two objects collide, if one thing has some mass and velocity, and say it collides with a second object which has mass times no velocity, suppose they stick together. In the rest of the sequence, then these two things are stuck together. Well, if we take the grand total of their combined momentum, we've got the momentum of the first car and the momentum of the second car, and those two have now stuck together. So we've got a combined mass 1 and mass 2 moving at some new velocity. So we can say that the total momentum before is equal to the total momentum after. And often, most of the time, in fact, when dealing with momentum in particular, after is denoted by a little prime, a little apostrophe up there. So the total momentum before the collision still has to remain after the collision. And so whatever the total mass is between those two vehicles, they are sharing that velocity in common. So the momentum afterward is going to be shared. So let's see how that works in this collision carts video. We're going to take a look at that in a second, but let's just take the values that were given. The initial velocity of 5 meters per second over mass of 3 kilograms. And let's set this other one to make life easier on ourselves. We're going to set this other one to 0 meters per second, and it's still going to have a mass of 1 kilogram. So our setup is going to look like, well, we've got the momentum of the first one plus the momentum of the second one is going to equal the momentum of the two of them together. So the mass times velocity, so we're going to have 3 kilograms times its velocity, 5, plus the mass of the second one, 1, times its velocity of 0, is going to give us a result of all of that momentum is going to be manifested in the two combined afterward. So their total mass is going to be 4 kilograms moving at some following velocity. So we got 15 plus 0 equals 4 times v prime. So v prime, the velocity afterward, should be 15 over 4. 16 over 4 is 4. So it's going to be 3.75 meters per second. And let's just see if that works out the way we think it should. What do I say? This one's going to be going at 5 meters per second. This one's going to be going 0, mass of 3. And this is what we call an inelastic collision. They're going to stick together. Start. There it is, 3.8. Okay, so it rounds, but 3.75 meters per second. All right, so that's the big idea of conservation of momentum. Now, let's break it down. Since we're mentioning elastic, inelastic, and explosion, let's get specific. So when we're talking about these three different kinds of collisions, we've got elastic, inelastic, and explosions. And if you learned about this as a freshman, we generally said that elastic collisions are those which undergo a bounce, and inelastic are those which stick together. But we're going to modify that description. We were kind of simplifying it. And so here's the way we're going to modify it. Elastic collisions are those which undergo a perfect bounce. I'll put that in quotes because perfect doesn't really have a physics meaning. However, when we say that something bounces perfectly, what we're really meaning is that the kinetic energy is conserved as well. I mean, momentum is going to be conserved, period, no matter what. Because when it comes to momentum, P equals mv, there's only one kind of momentum. There's only mv, as opposed to energy, where we've got kinetic energy, we've got gravitational energy, we've got spring energy, we've got heat. When things collide, total energy is conserved, but sometimes kinetic energy could be lost. I mean, you can take two objects that are coming from opposite directions, they each have energy and they crash. Clearly, there's no kinetic energy remaining, but some of the collision is going to result in sound and heat due to deformation of the parts. So the total energy is going to be conserved. But what differentiates a generic collision from a elastic collision, sometimes called perfectly elastic, which is a little bit redundant because elastic implies it's a perfect collision, but that means that the kinetic energy is conserved as well as momentum. And so an inelastic collision is anything where any kind of collision where some kinetic energy is going to be lost. The amount of kinetic energy is going to be less than what you started with, and so essentially we're left with a little bit less information. Elastic collisions, kinetic energy will equal before and after, and the momentum will be equal before and after. Whereas with inelastic collisions is one where the momentum is definitely conserved, as it will always be, but that's about all we know. And then lastly, we've got explosions, which is often where we got something like two objects that are stuck together, then burst apart. Say, like if they're spring-loaded or a firecracker, or something that's intact, then blasts into a bunch of different pieces, all go in different directions. So that's going to go that way, and that's going to go that way. And, suppose that beforehand, if the momentum was 0 before the explosion occurred, then the sum of the momentums has still got to be 0, which necessitates that if one has some positive momentum, the other one is going to have an equal amount of negative momentum. If we were to add those two together, you'd still have no momentum. So let's look at some examples. Cards collide inelastically and stick together. Not only is kinetic energy lost, but they're going to combine. So we got this card on yellow crashing into a blue card. The mass of the yellow card number 1, is 0.5 kilogram, and card number 2 is 1/4 kilogram. The velocity of the first card is 2 meters per second, and the velocity of the second card is 0. It's at rest. What will the velocity be of the combined objects? So we're going to have momentum of 1 plus momentum of 2 equals their combined momentum afterward. So we got m1 v1. This is where we start getting into all of the notation. We're going to get very used to m1 v1, etc. So m1 v1 plus m2 v2 equals m, we call it total, v prime. I suppose if you wanted, you could call it m1 plus 2. You could call it m1 plus m2 combined v prime. That's nice. All right, now let's plug some things in. So the mass of the first one is 0.5 kilograms going at 2 meters per second, and the mass of the second is 0.25 moving at 0. And the total of their masses is going to be 0.75, and they will be moving at some v prime. So that's 0. So we got 0.5 times 2, that's 1, equals 0.75 v prime. Because I can't talk and think at the same time, I'm going to use a calculator for this. 1 divided by 0.75 1.3. Okay, so the velocity afterwards is going to be 1.33 meters per second. So when two carts collide elastically, as we mentioned a few minutes ago, not only is momentum conserved, but also kinetic energy is conserved. So that brings up a possibility of a lot more math. So for this problem, we know that the what do we say? The mass of the yellow cart is 0.5 kilograms, and its initial velocity was 2 meters per second. The mass of the second car is 0.25 kilograms, and its initial velocity is 0. And for a question of elasticity, the question could be asked, what is the velocity of both cars after the collision? And you might think, well, how am I supposed to know? I need to know the velocity of one car after the collision in order to know the second. Because you're thinking, I got two unknown variables. And that's exactly why elastic collisions get more mathematically involved, because you're going to have two equations to solve for both of those collisions, both of those final velocities. So we need to break it down into the momentum side of things and the kinetic energy side of things. So let's do that. As far as momentum goes, we would have the first cart, m1v1, plus the second cart's momentum equals, and now because they're elastic, they're going to bounce off of each other. We're going to have m1v1 prime plus m2v2 prime. Separately from that, we need to evaluate the kinetic energy. And if we are told specifically that it is an elastic collision, then we know for a fact that the kinetic energy is conserved. So that looks like this. 1/2 m1v1 prime squared. This is where the nomenclature gets really busy, but every piece of information matters. Plus 1/2 m2v2. You know what? I goofed. It's not prime yet. It's still before. So m1 1/2 m1 v1 squared plus 1/2 m2 v2 squared equals 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared. And one thing you can pretty reliably do if you have both of these is, if you're solving for the final velocity, you can cancel all these 1/2s. Sometimes the question might be different. The question might say, what is the kinetic energy before and after? Well, if you knew the velocities, you better not cancel the 1/2s, because 1/2s are part of the kinetic energy formula. If you're being asked, what are the final velocities? Well, now we've just got a whole bunch of algebra in front of us. M1, we got, so that's 0.5 times V1, 2, plus M2, which is 0.25 times V2, 0, equals M1, so that's 0.5 times V1 prime, plus M2, which is 0.25 times V2 prime. And then over here on the kinetic energy side, we've got M1, which is 0.5 times V1 squared, so that's 4, 2 squared is 4, plus 1/2 of M2V2 squared. Its original velocity was 0, so that's still 0, equals the first mass, 0.5 times V1 prime squared plus 0.25 V2 prime squared. And as you can imagine, you gotta keep going. You gotta keep digging down from there. Now, as you can tell from the minutes that it's taken to explain this far, there's a lot of math. And AP folks on the test, they're not interested in just having you do 10 minutes of math. And so, more often, the question will be something like this. If it is observed that V1 prime is, 0.66 meters per second, and V2 prime is 2.66 meters per second, is it elastic? So that's what I mean by check for elasticity. You may be given the final velocities, or you might be given enough information to more quickly find the final velocities, and then you will be asked to evaluate if it was elastic. Essentially, that's checking if you know what elastic means. Do you know that to be elastic means to conserve the kinetic energy? And so there's a lot less math, because now all you have to do is check to see if kinetic energy before equals kinetic energy after. So 1/2 m1 v1 squared plus 1/2 m2 v2 squared equals question mark 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared. All we care about to answer the yes or no question is, does the left side equal the right side? We can cancel out all the halves. So we got m1, which is 0.5 times v1 squared. So the original velocity was 2. 2 squared is 4. And that was 0. And on the right-hand side equals 0.5 times v1 prime squared. All right, so times 0.66 squared plus mass 2, 0.25 times v2 prime, 2.66 squared. Are those two sides in fact equal? All right, so 4 times 1/2, that's 2. Does 2 equal 0.66 times 0.5? That's 0.66 squared times 0.5. 2178. 0.2178 plus 2.66 squared times 0.25, 1.7689. All right, so do these two combined equal 2? Yes, they do. They approximately equal 2. So yes, I can evaluate if they were in fact elastic. All right, so it's quite busy, elastic collisions. Conservation of momentum in 2 dimensions. Same as 1 dimension, but you got to do it twice. You've got to separate each direction. So, which is to say that the total momentum in the x direction is constant, and the total momentum in the y direction is constant. So each of their individual directions are independent. So let's take a new example, an explosion, and something that occurs in 2 dimensions. So we got a 1 kilogram ice hockey puck with a firecracker embedded. So some yellow. That's the sparkle. Is currently sliding along the ice at 10 meters per second. So it's got a velocity of 10 meters per second and a mass of 1 kilogram. And so we're told that after the explosion, some piece of it goes in one direction at 3 meters per second at 45 degrees below the line of its original motion. So this piece is going to go down this way, and we would like to know what direction and speed the other one is traveling at. So let's consider it. Let's consider the x by itself in the x direction. We can say, well, because we've got all of this momentum in the x direction originally. So the momentum before is going to equal the momentum after. The momentum before is, well, there's only one object, so m times v. And afterward, there's two objects. So we're going to have, let's call this one piece number 1, and this is piece number 2. So we're going to have m1 v1 prime plus m2 v2 prime. Well, the mass of the whole piece was 1 kilogram, and it's moving at 10 meters per second. So there's 10 units of momentum, 10 kilogram meters per second. And afterward, we're told that 0.6 kilograms of it is moving at 3 meters per second at 45 degrees below the line of its original motion. So it's going at 3 meters per second down that way at an angle of 45 degrees. So for only talking about the x direction, we've got to split that velocity, or split that momentum. No, I guess we'll split that velocity into x and y components. So this piece, which was going at, maybe I'll make it look more 45-ish, going at 3 meters per second at 45 degrees, then we've got two components. We've got the velocity in the x direction and the velocity in the y. So that's going to be the velocity of piece 1 in the x direction is 3 cos of 45, and v2, v1 in the y direction is going to be 3 times sine of 45. This turns out to be 2.12 meters per second, and if you're good with trig, you'll realize that because it's 45 degrees, the other one's also going to be 2.12 meters per second. So this is going at 2.12 meters per second, and so that leaves us, I think, enough information to find the velocity of the other piece in the x direction, because the total horizontal momentum has to remain constant. So if one piece has some of that horizontal momentum, the other piece has to have the rest of the horizontal momentum, the x momentum. So the other piece, well, if it broke into two pieces, it started as 1 kilogram, and 0.6 kilograms is one piece, then 0.4 kilograms has got to be the other piece, v2 prime. So 0.6 times 2.12 is 1.272 plus 0.4 v2 prime. All right, so let's figure that out. So minus 1.272 from both sides, 0.4 v2 prime, and I should, continually remind ourselves that this is only the x direction. So 10 minus 1.272 is 8.728. Divide both sides by 0.4, and we get v2 x prime is 21.82 meters per second. So what is that back in our diagram? That is this one's x velocity, v2 x prime. I'm realizing, I suppose, that we could put primes here because those are all after the explosion. So that takes care of one of the after velocities, the x component, and we also need to figure out what it's going to be in the y direction. in the y direction, it's the same math, same setup. The momentum, the mass times the velocity in the y direction equals m1 v1 y prime plus m2 v2 y prime. Now, if I was being fully coherent with all of the subscripts, I could have put x's here and here, x's throughout, x's throughout. So in the y direction, well, how much momentum was in the y direction? Well, initially it was only moving horizontally. How much of that is in the y direction? 0. So there is no momentum in the y direction, which means if some piece gets blasted downward, the other piece has necessarily got to be going upward with some velocity, and just the right amount of velocity so that the momentum of those two pieces still adds up to 0. So m1.6 times v1 prime y times 2.12. It's going down, so that makes that a negative. And the momentum of the second piece is going to be 0.4 times v2y prime. So 0.6 times 2.12. I knew that already. So 0 equals negative 1.272 plus 0.4 times v2y prime. Move that over to the other side. So 1.272 equals 0.4 times v2y prime. Divide both sides, 0.4. We get v2y prime is 3.18 meters per second. So now we have both the x and y components of the other piece. So that other piece, that top half of the puck, is going to the right at pretty fast 21.8 meters per second, and it's moving upward at 3.18 meters per second. And we can then take those two velocity components and recombine them. So the velocity is going to be the root of 3.18 squared plus 21.8 squared. Velocity is whatever that's going to be, and the angle of its travel is going to be the inverse tan of opposite so that'll be 3.18 over the adjacent 21.8, and you get an angle of whatever that is. So I hope this walkthrough helps paint a picture of how to handle some conservation of momentum problems and the particular meaning of what it means to collide elastically, because that's the kind of the big new piece. Right? Good luck. Sorry, what?